Alex was saying, we're moving from rust to stainless steel in a way. I'm giving you a prequel of something that you'll hear more about, or maybe even less about, on Wednesday. So here I decided to give you some kind of tour from kind of the basics that were kind of uncovered like 20 years ago to what we tried to make out of it in the last couple of months. Right. What is ordered logic? So if I had known that Thiemann, where is he, did say in the last session, I could have said it more shortly. So ordered logic is a substructural logic. And here I have those nice rules of weakening, exchange, and contraction. And in substructural logics, it's actually a game that you play with turning on and off these rules, right? And usually we are here in this realm of intuitionistic logic, where you have all those rules, weakening, exchange, and contraction, and that's pervasively used in programming languages. Then, oh, there is a reference to Rust even. Then you have a fine logic, where you have weakening and exchange, but no contraction, and Rust is, I guess, the most prominent perpetrator here. Then you could also have a combination of exchange and contraction. I didn't know an example of that, but Thiemann presented one in the last session. So if you missed it, you should definitely look at the recording. Then if you just have, if you only have exchange, then we are talking about linear types, and there is plenty of stuff there, linear Haskell, session types, lots of theory around. Now if you turn off everything, then you end up in ordered logic. So basically, everything lives sequentially in your context, and you can only consume it like from left to right or right to left. And that's what we're going to look at now. Actually, I have to transport you back like 20 years to when Jeff Polikoff and Frank Fanning kind of popularized it, made it useful for computer scientists. So they looked at non-commutative linear logic. And essentially, they developed a proof theory for an ordered linear lambda calculus. And their intended application was really theoretical. They were looking at logical frameworks. And if you look at the later papers of Jeff, subsequent papers of Jeff and Frank, you'll see that's the direction they were aiming for, like these logical foundations. And if you know something about linguistic, then maybe you know that there's a connection to lambda calculus. So that's about parsing and natural language. Now, what does this give you? Actually, it gives you a proliferation of types. So you don't have just one implication. You have 4 of them, right? So now I'm quoting actually from the Polikoff and Fanning paper. So they actually make a distinction. They have intuitionistic assumptions, they have linear assumptions, they have ordered assumptions, but there you actually have to make a difference if you are allowed to take your assumptions from the left end or from the right end of your assumptions. And that gives you 2 different implications. Yeah, one puts the argument at the end of the ordered context, and the other one puts it at the beginning. So you have different reasoning principles there. Additionally, that's not in Frank's and Jeff's paper. Most systems that are like programming oriented, they also have products. And there you also have 4 products, right? You have intuitionistic product, you have linear tensor, that's the one from linear logic, and then you have left ordered and right ordered. I'm not sure that there are any sort of standard symbols, so I just picked some that look. So there's actually something that's for right ordered that's used, but I just picked some symbols here. Right, and I guess you already guessed it. Now that we have 4 different implications, well, you also have 4 different lambdas and 4 different applications, just fitting to those types. And you have also 4 different beta reductions. If you squint, they all look like the same, but formally they are all conceptually they are all different. And if you notice here, you also have different variables, x, y, and z. That's because in Jeff and Frank's paper, you have different contexts for the intuitionistic variables. These are the x's, the y's are the linear ones, and the z's are the ones that denote assumptions from the ordered context. So that's what it looks like. So you have these 3 contexts, and Yeah, so you can really see it's geared towards a theoretical treatment. So in a practical language, this is a no-go that you have several contexts. I would say. Right, and just to show you something here, and actually here. So this is don't read the text. So I just stole it from their paper. So this is which implication is it? So this is one of the lambdas. Let's just say it like this. Essentially, this is one of the ordered ones, and what you can see here is you are defining the abstraction in an ordered context here. Everything else, the unrestricted and the linear stuff, is just kept as it is, because everything that's ordered is also linear. Yeah, remember, for ordered assumptions, you have no rules, no substructural rules, and here we are putting the new assumption at the end of the string of assumptions. Right, and similar, if you invoke such a function, then essentially you are allowed to split the ordered context somewhere in the middle. You can derive the function with one half. You can derive the argument with the other half. And notice here, the argument has to be derived with the second part, the later part of the assumptions. And now I don't have to show you the left-ordered functions because you just swap this around. So you can imagine all that. By the way, just to not leave that unexplained, that's the usual kind of distribution operator for linear contexts, which just interleaves assumptions from delta 1 and delta 2 without duplication and so on. All right, let's now take a step towards programming. So we're moving from, I think that was, it was some I assume that was from the Lambeck Festschrift. So this is about programming, right? This is a Poppel paper from 2003 by Patterson and friends, and they actually talk about a type theory for memory allocation and data layout. So, well, their application here is memory management, and they have a different interpretation of ordering. And we will come back to that because that's actually the crucial thing. Their interpretation of ordering is physical adjacency of memory blocks. And they actually want to reason about the size of those memory blocks. And they have a product, they call it the fuse operator, and it's the left to right product. Because it's kind of, if you do a stack allocation, it's kind of rare to first talk about the stuff on top of the stack and then put something below and then put some stuff further below. So therefore, they only look at one of those products here. Right. Let me get now to the stumbling stone in their interpretation as compared to the earlier work of Jeff and Frank. So this is a sound rule for a hypothetical let construct in the ordered lambda calculus. And I'm calling ordered lambda calculus the lambda calculus that we just saw from Jeff's and Frank's work, right? So here we have some sort of term m that we want to abstract into a and then use that in m prime. So now here we have the ordered assumptions. So, and interestingly, we can take the assumptions that we use to prove m, we can take them out of the middle of this ordered context, right? So executing m sort of squeezes the assumptions omega, consumes those assumptions in omega into this tiny tau here. And then we replace it actually here in the middle after omega 1 and before omega 2 and put it there. So that's entirely fine in the ordered lambda calculus because the interpretation of order is just about reasoning preserves the relative order of hypotheses. So if you find any stuff that can react in the middle of your list of hypotheses, so if you think in terms of sequence, for example, then you can just squeeze it. You can just reduce it in the middle, right? Unfortunately, if you want to reason about memory, this rule is no good. Just consider an m here of unit type. So that means m here consumes some memory that's denoted by omega, some non-empty memory, and then it's in the middle between omega 1 and omega 2. So the size of unit is 0, right? So that means we take something, we delete it, so now we need to kind of move omega 2 back and align it again. So that's not really a good idea. Yeah? So this is not good for reasoning about memory adjacency. So they make this observation that a rule like that is not size preserving. They need more control, and so they go off and develop a different calculus, which they call the orderly lambda calculus, which does this right. Okay, now we move actually only a couple of days, I guess. So TLDI used to be a workshop conference, which was kind of co-located with Popple. I don't know, I didn't check if it was like 2 days before or 2 days after, but something like that. It's about the same time. So this is by Amal Ahmed and David Walker, Logical Approach to Stack Typing. And if you look here, it's a logic that's aware of consecutive blocks of memory. That sounds quite close. Essentially, it's pretty interesting because if you look at the logic that they define, it's pretty much a separation logic that's defined in that paper, only that 20 years ago you didn't call it separation logic yet. But it's actually a separation logic, and you find everything like separating conjunction and magic wand, that's there. And then they have versions of separating conjunction and magic wand that are aware of this consecutivity of memory. So that's what they are putting there. That's the logic part. And then they put it to work in a typed assembly language. My guess it was a bit too much for the Popple committee to accept there, but you never know. But they had some key technical innovations that are quite interesting and also useful in our work. So instead of having separate typing context, which we already ruled as being a bit impractical in a real language, they actually introduced, well, they kind of reinterpreted bunched typing contexts. So that was an innovation that's due to the logic of bunched implications by O'Hearn and Pym. And the idea is essentially that your typing context is not a linear thing, but rather it's a tree structure. So it can be empty, it can be a single assumption, or you can have two different context formers that concatenate or separate different contexts. And in this case, you have one that's unordered, that's the comma and linear, and you have an ordered separator. And that's kind of the less pleasant thing if you work with that in a proof or something. These guys have a non-empty theory. So you have a commutative monoid that is formed from the empty context and the comma operator, because these are like the linear assumptions. And if you only have comma in your context, then this is like behaves like a linear context. And then the ordered separator is just a monoid with the empty context. And again, if you only have semicolons, then you have a pure ordered logic assumption. Right. And then they also have something that they call disorder. So ordered assumptions can be relaxed into an unordered one, which means whenever you can prove something with an ordered assumption, then you can also prove it with an unordered one, because usually it doesn't depend on that. And this is really application dependent. Right. Okay. They have some rules. So this is a similar rule. Do I want to go into that? Yeah, so just to show you, let's not look at the introduction rule, which isn't really difficult. Just as an example of what things look like with these bunched contexts. So this is the fuse elimination rule. So it's the elimination rule for ordered pairs. And actually, it's just the pair elimination rule, sorry. But essentially, if you would write a syntax for it, it would be a let xy equals, and then you would pick up this, the value of this one here, and the C would be proved by the let, and here you would be typing the body of the let, right? Now, what you can see here, the point here is we have remember we're talking about bunched context, so this thing here is tree structured, right? So this gamma here is actually a tree with a hole, and inside of the hole I find the context delta, which I use to prove that that pair here, that I use to evaluate that pair. Now then I have the values for F1 and F2, and I bind them to two new variables, u1 and u2, and I put them back at the place where I took the context before. So it's essentially a generalization of the let rule that I showed you a couple of slides back. And here, this is just really, really nice. And essentially, you're returning, and this would also make sense for this kind of memory adjacency, because essentially we are returning the pair in adjacent memory chunks, right? So if you imagine the pair lives in adjacent memory locations, then here we're just putting a border in between. But the adjacency doesn't really change because we're not changing the structure here. Right. Let me get to the second part now. How do we need to change this? How do we need to reinterpret this to talk about type state? To do that, I remind you of which talk was that? I think was like the second talk in the morning that also had this example. Well, it's a standard example, so everybody has it. So let's consider an API here for files. That's really the standard example. Open returns a handle. Then we have read, write, and close operations that each take a handle. Either return something interesting from the file content or put something into the file. Last but not least, we have a close operation, and that's supposed to close. Now, the idea of type state in this context here is after you close the handle, you would like to make sure that nobody is going to read or write from the same handle again. To do that, we are encoding type state essentially by the set of traces of future operations that are admissible on the handle. Now, so if you look at here, the handle type that is returned by open, you could, if you remember the last session, we talked about, I think Colin talked about capabilities. You could consider this a capability in a way that says, hey, on this handle you can do read or write arbitrarily often, and then you have to close, right? That's what it says. And then you can also see here, in order to read, you need a handle that has the capability to read once. To write, you need a handle and so on. And to close, you need a handle that has the capability to close. Right, and then in this case, you can really encode it in this kind of finite automaton way, where essentially, as long as you do a read or write, you remain in this open file state. Once you do the close, you're ending up in epsilon, and then the file is closed, and obviously in that state you cannot perform any of the further operations anymore. Right, now, how do we put ordered logic, ordered typing to use in that context? The point here is we are going to interpret the contextual order as a temporal order. So if I find two assumptions with a semicolon, it means I must consume Z completely, the resource that's hanging onto Z completely before I start processing Z prime. In order to do something like a borrow, I need to apply a split primitive that returns an ordered pair. So that looks like this. Suppose you have a handle that's described by these future traces R, then split returns an ordered pair, where the first component is some R1, and usually that's what you are asking for the borrow to be. And then it will, the rest will be some R2, such that the concatenation of the two is a subset of R, which means after you put, so if you call this the borrow and that the leftover, after you put them back together, then you're still adhering to the overall protocol of the initial resource. If you apply that to file handles, then you could say R here is a borrow if R is just a subset of RW star, because, well, you can't close it. So you don't have the capability to close here. You can read or write as often as you want, but no closing. If you have a language that ends with C, then that kind of tells you this is an owning reference. Actually, this is also a linear reference because you're not allowed to drop it, as it's the owning reference, and you can apply close to that. Moreover, it can be dropped, so the handle can be dropped as soon as epsilon is an element here, because that means, as soon as epsilon is in the handle language, then it's an affine reference, and if you don't use it anymore, then you can just get rid of it. So here I have a couple of examples. So here I'm assuming I have an open file handle. I have to look a little bit at the time, I guess. And if I split it in this way, so here I'm annotating it in order to make it more explicit. If I want to split off a read-write borrow, then this type here at which this capability at which I'm splitting always ends up here in the type of the borrow. That's the way that things are set up. And then it turns out that you can always calculate a best possible leftover type here. So there's an operation that's called product derivative. I mean, if you look at regular languages here, and then you can really there's a uniquely defined best continuation here, so that this inequation that I showed you on the previous slide holds. But you can also take read-only borrows. In this case, the leftover is the same as before. And you can also take some sort of a final borrow, because my close operation, if you remember, the close asked for a handle that just has the capability C, right? So in order to use that, I first have to split at C, then I get a handle that is just ready to close and nothing else. And the leftover has type epsilon, has capability epsilon, so the only thing I can do with it is I can drop it. And that's all. Right. Now, I guess I don't really have time to go over this rule again. Well, I can not go over the examples, but I can go over the rule. So this rule is actually okay in our calculus if we make some extra assumptions. Namely, there are 3 different ways in which this rule can be okay. The first one is if omega is empty, right? If omega is empty, then the only thing that can happen inside of M, it can allocate new resources. So if tau contains any sort of resources, they have to be fresh, because I didn't feed anything in. So that means I can put it safely in the middle of this context, although I wouldn't really want to do that. So this should be semicolon, sorry. But I wouldn't want to do that, because if I return resources here, they are independent of anything that I had before, so I could actually put them in parallel. So I would use the other context former. Or the other alternative would be if M here performs no operations on resources, so you could say it's free of effects, then it's also fine, because then I'm not using anything. I'm not performing any actions of stuff in omega. The only thing that M can do is kind of pass it through unchanged. For example, if I kind of eliminate a pair and then just put it back together, I sure want to do stuff like that, or just rearrange things. So that's fine. Unfortunately for that, we will have to introduce an effect system, which I won't get to here, but a very simple one. Maybe you could get around by that by doing a calculus based on call by push value. Then you have this notion of generalized values. Then you could say, okay, I'm just allowing generalized values here, but we didn't do that. Or if omega 1 here, if this guy here, if it's empty, well, then it's also fine, because all that we want is we need to first process anything in omega 1 before we can start processing stuff in omega. If omega 1 is empty, well, then we can start dealing with stuff in omega right away. All right. Right. So if you count it right, well, it's there. That means you would like to have 3 different let operations that allow you to kind of put things in the right way back into the context. For the sake of time, so these are the ones, I'm not going over them. I'm going to the summary. So I told you a little bit about ordered logic, that what happened mostly 20 years ago. And the key difference between the different applications is really that there are different interpretations of this order. So kind of the first one, the logical one, is you just talk about the relative order of hypotheses. Then there's work that is using memory adjacency. And in our work, we kind of did another reinterpretation. We also are doing a reinterpretation of these bunch contexts so that we now, the semicolon stands for temporal order of consumption. And that's really a good fit for Typestate with a notion of borrowing. And compared to other work, like alias types and so on, it really avoids complications that arise if you make object identities explicit. That's really super annoying because then you have to introduce universal quantification over identities. And actually, we tried that in some previous work, and it really gets very messy to do that. So the key ingredients here is that we are interpreting Typestate as a set of traces of future operations. You have this kind of very simple splitting operation, and then also using these bunch contexts with a temporal interpretation. We feel that these are like the key points of our work. Well, and more on that. See you on Wednesday morning. Thank you.
So Peter, I didn't quite get the second bullet. Maybe it's jet lag, or maybe that's just
which one? This
one
or this one?
No, the temporal is a good fit for Typestate with borrowing. So can you sort of re-expand? So you had three forms of borrowing, right? In this.
Actually, no. It's just this. So there is just a single element that you can use in order to implement borrowing. And that's this split operation.
Okay.
And it's really, everything is in the split operation. And the key of the split is that it returns an ordered pair. Left or right ordered, whatever. I mean, it's processed from left to right.
Right.
And that's the key thing. And right.
Right, but the borrowing that you do have, it relaxes the linearity, does it?
It relaxes what?
The linearity, so you can have multiple references to the same thing at the same time?
You do have, so the operational interpretation is that you just duplicate the same reference.
Yeah.
The two aliases, they can have different substructural properties depending on the capability index that you've got.
Right.
Yeah, so as soon as the capability index has this epsilon, or the unit, then you can drop it.
Yeah.
Otherwise, if it still has, so if unit is not contained in the language, then then it must be linear.
Right. So
and essentially, if it's just epsilon, then it's unrestricted, and the only thing you can do is drop it. I mean, we have this RW star. That would be a fine. So you can use it or not.
Right. But if you had a type state where you, like, let's say we are mediating the file between open and closed or something like that, then like the typical problem when you add borrowing that relaxes linearity is to kind of propagate the type state view or the sort of the type state of the object to the view of the individual references. And that's the bit that I'm missing from. But maybe we can take that off.
Yeah, I mean, we can. You mean like here? So if you were kind of splitting off the R star.
Yeah.
Right. So typically, I mean, usually what the context in which it would happen, you would have you would invoke a function on this B. The argument of this function would be this R star. That would be a fine reference. You can read on it as often as you want. And then you can drop that. And the point of the ordered product is that you first have to process this B entirely before you can start with H.
Okay, got it.
Right, and that's what the type system really enforces.
Right.
Okay. And the point is really that this ordered mechanism and the structure of the context enables you to do that without talking about object identities, which make things annoying. All right.
So I'll stand up so you can see me. This was very cool. I think this use of bunch contexts for ordering like this makes a lot of sense. What I'm trying to still see a little bit more the relationship between this and then the time you spent talking about this problem with trying to take sort of implication in the middle of the context. And part of this is I'm thinking of this, you talked about memory regions and things like that, and so this seems analogous to the lambic calculus categorical grammar case, and there they play the kind of, weird from a PL perspective approach of no unit types, right? And so you can't have things disappear or appear, say, in their case, in the middle of a sentence. Does it make sense to do something similar here? And just say, like, you can't do, for spatial things, unit.
I have to admit I didn't think much about spatial things until I ran into this related work, but maybe we can discuss it offline. That's the best I can offer right now.